My name is Gretchen Hinger, and this is my Physics 2211 Lab 1 on constant velocity. Looking over this lab, we're going to be discussing the introduction and purpose, physics concepts, tracker observation, the code, the data comparison, and final questions. To introduce this lab, it was basically about an object being in constant velocity, and then looking at that object's motion through a tracker software, then comparing that to a computational model using coding, and then taking that comparison to gain an understanding of the following physics concepts that I will talk about in the next slide. For this experiment, we covered many physics concepts. The first one is Newton's first law. This law says that an object at rest will stay at rest, and an object in motion will stay in motion unless a force acts on the object, which in this case, the ping pong ball initially has a force act on it and then reaches constant velocity when the tracker is looking at it. The second law we're looking at is Newton's second law. For this experiment, this is important because there is no force on the object during the constant velocity time that we are looking at in the experiment. So that means with no force, there's no change in momentum, no acceleration, which all still means that there can be a constant velocity and it can still be in motion. For this experiment, we'll be using two equations from these laws. The first equation being the one in the top right, which is the position update formula. This has that the velocity average times the change in time plus the initial position equals the final position. For this, instead of the average velocity, we'll be using the initial velocity found in the experimental model. The second equation that we can look at from these two laws is the final velocity equation in the bottom right. This means that the second velocity will equal the initial velocity plus the F net over mass times change in time. This shows that because there is zero net force, the velocity will stay at the initial velocity in theory for the entire time that the ball is in motion. Moving on to the actual experiment, we can see in the tracker video that the ball is moving across the x-axis. While I accidentally did move it a little in the y-axis due to my terrible ability to add a straight force, we will not be taking that into account. For this, each time step is a 30th of a second, which will be used later on the computational thing, with the initial position being 0, 0, 0, and the initial velocity being 0.42 meters per second, found by taking the first and second time step and using the average velocity of that. Then, the experiment is conducted over 0 to 1.1 seconds. Along with this, the ball is the system, and the surroundings are the table and everything else around it. Moving on to the computational side of this experiment, with these two codings seen on the top and bottom picture, you can see that at the very top, where my arrow is, I left the time to be up to 1.1 seconds in order to take into account all of the time that also the experimental data covers. Using the starter code, I changed a couple things, like the initial velocity of the position update formula to be 0.422, which is what we initially found in the experimental data, then changed the position update formula to reflect the position update formula we had in the physics concepts. Then I changed the delta t to 1/30th of a second, like the experimental video, and then from there I changed the ball velocity to the 0.422, like I had earlier. For this, because we don't have any force, the ball's mass will not equal anything that is relevant to the experiment, meaning that we can just leave that as 1. Looking at the experimental and computational data, we can see that there's a good bit of difference in these two. This difference can be explained by the fact that there is friction going in the opposite direction of the original force on the actual experimental ping pong ball. Due to the fact that the system we cannot take out the force of friction or the air resistance, that will still take effect on the actual ping pong ball compared to the computational data that does not take that into account. Finally, to end off the video, we're going to cover the what if and what does it mean questions. For the what if question, if we change the positive x-axis to the negative x-axis, this would just reflect the graph over the x-axis, making it so that the slope of the graph will change to negative of what it is now. But the velocity will still be constant in just the negative of that, with the same magnitude. For the what does it mean question, we cannot clearly determine all the forces that make it so that there is no net force and so that it has a constant velocity. In the y-axis, there's obviously the normal force and the gravity canceling out, but for the x-axis, there's really no net force, and there's friction and air resistance in the opposite direction of movement, meaning that there are also probably other forces that we don't know about. That covers all of the constant velocity lab for Physics 2211, lab number 1. Thank you for watching.